Hi folks, the following video is our second one on reactivity. I'm going to start talking about organic reactions in today's video. I'll talk about what are known as nucleophiles, electrophiles, and general patterns for curved arrows. Most of the reactions you'll encounter in organic chemistry are what are known as ionic reactions. These involve the appearance of ions as either reactants, intermediates, or products in your reaction. Ionic reactions are going to occur if you have a reactant that has a site of high electron density. We'll term this reactant the nucleophile. And you also need a reactant that has a site of low electron density. This will be known as the electrophile. In the nucleophile, look for an electron-rich site. You could also call this a nucleophilic site. The nucleophile is going to donate a pair of electrons during the reaction. And recall that this is also the function of a Lewis base that we saw back when we talked about acids and bases. For your nucleophilic sites, or electron-rich sites, be on the lookout for lone pairs or pi bonds. Here are some example molecules that all contain nucleophilic sites. In the alcohol molecule, you'd say that the oxygen with the lone pairs is the nucleophilic site because that oxygen has lone pairs that can be donated and it has a partial negative charge. In the anionic alkoxide, shown to the right, the oxygen again is the nucleophilic site. This is your site where you have electron density in the form of lone pairs that could be donated to form a new bond. In the case of this carbon-lithium molecule, carbon is more electronegative than lithium, so this central carbon has a partial negative charge. This carbon with that partial negative charge is the nucleophilic site. And for the alkene shown below, the pi bond has electron density in it that's above and below the plane of the molecule, and similar to a lone pair, that pi bond can also serve as a nucleophilic site. In contrast, electrophiles will contain an electron poor site, known as an electrophilic site. The electrophile can accept a pair of electrons, and this is the same function that we saw when talking about Lewis acids previously. Be on the lookout for atoms with a partial positive charge or incomplete octets for your electrophilic sites. Here are some example molecules that contain electrophilic sites. In the alkyl halide, the carbon-chlorine bond is polar, with chlorine being more electronegative than carbon. It is this carbon with the partial positive charge that is the electrophilic site in this molecule. If you have a carbon with a positive charge, that's known as a carbocation, and that carbon has an incomplete octet and is therefore that molecule's electrophilic site. And similarly, a boron with 3 bonds and a neutral charge also has an incomplete octet and an empty p orbital, so that boron would be the electrophilic site of this molecule. Now that I've introduced the concept of nucleophiles and electrophiles, I want to talk about mechanisms. Mechanisms are the exact steps by which a reaction takes place, and we will use curved arrows in our mechanisms to show the flow of electrons, where the electrons are going or coming from in order to form new bonds. An example of a mechanism that we've already seen are acid-base reactions. Here I'm showing a general acid, HA, a base, B-, and these react together in a mechanism that has two curved arrows. I used the lone pair from the base to form a new bond to the proton, and I take the electrons from the HA bond and bring them to A. I form my conjugate base A- and conjugate acid HB. The arrow tail always shows where the electrons are coming from. This is either a lone pair or a bond. And the arrowhead shows where the electrons are going. You want to be very careful about precisely how you draw these curved arrows, because organic chemists use these to communicate information about the reaction. For the remainder of our video, I'm going to show you 4 curved arrow patterns that we're going to use for the remainder of the semester. These patterns can be classified as nucleophilic attack, loss of leaving group, proton transfer, or rearrangement. I'll go through these one at a time. Nucleophilic attack involves a nucleophile using electrons to form a new bond to an electrophile. This is similar to a Lewis acid-base reaction that we've seen previously. Let's consider this reaction where I'm showing you an alcohol and a carbocation. These molecules react with each other to form the following product. Notice my central carbon of the carbocation got a 4th bond to oxygen, and now the oxygen has 3 bonds, a lone pair, and a positive charge. To figure out how I made this new carbon-oxygen bond, I want to first identify my nucleophile and electrophile. The oxygen with lone pairs can serve as the nucleophile, or electron donor, and the carbocation central carbon with the positive charge is the electrophile. This carbon has an incomplete octet, and it will react in order to achieve a complete octet at carbon. For this particular reaction, the nucleophilic attack mechanism is going to involve a single curved arrow. I take an oxygen lone pair of electrons and bring them to the electrophilic carbon, the carbocation itself. The curved arrow is meant to indicate that oxygen is sharing its electrons with carbon. That lone pair isn't hopping over there. It's going from a lone pair and becoming a bond. Now let's consider another example. I have an amine as well as a ketone. And here I'm giving you the product of the nucleophilic attack. Notice I have a new bond between nitrogen and carbon, and I've gone from a carbon-oxygen double bond to a carbon-oxygen single bond. Similar to the first example, I'm going to begin by classifying my molecules as nucleophiles or electrophiles. The amine molecule I'll classify as a nucleophile because the nitrogen could use its lone pair to form a new bond. And the ketone molecule is more complicated. It contains both electrophilic and nucleophilic sites. Because of the polar carbon-oxygen bond, carbon is partially positively charged, making it electrophilic, and oxygen is partially negatively charged, making it potentially nucleophilic. Because I determined that my amine molecule would best serve as a nucleophile, I'm going to focus on this electrophilic carbon site for my reaction. To get from my reactants to my product, I'm going to need 2 curved arrows for this particular nucleophilic attack. I take the nitrogen lone pair and bring it to the electrophilic carbon, and I break the carbon-oxygen pi bond and bring those electrons to oxygen. The first curved arrow is showing nitrogen sharing its electrons with carbon to generate that new nitrogen-carbon bond. To avoid exceeding this central carbon's octet, I have to break the pi bond and move those electrons to oxygen at the same time. The second curved arrow is the one that gets me to this carbon-oxygen single bond, and it makes a new lone pair on oxygen. I strongly recommend not trying to memorize how many curved arrows are involved, but looking at each example as its own unique situation and figuring out how many curved arrows that example calls for. The second curved arrow pattern is known as loss of leaving group. This is essentially the reverse of a nucleophilic attack, and I'll show you what I mean by that. In the loss of leaving group, a group from your molecule is going to depart with the electrons from a polar bond, meaning that polar bond breaks in this reaction step. The term leaving group refers to the group that gets the electrons from that bond, and you're going to give the electrons from the bond to the more electronegative atom. Let's consider this tert-butyl bromide alkyl halide starting material. In the loss of leaving group step, the products from this given starting material would be a carbocation and bromide anion. Notice in my reaction, my carbon-bromine bond has broken. In this case, the loss of leaving group would have a single curved arrow from the middle of the carbon-bromine bond to bromine. This arrow indicates that I'm taking the electrons from the carbon-bromine bond and giving them to bromine. And here's a different example of what a loss of leaving group could look like. In this starting material, I have a carbon with bonds to an oxygen as well as a chlorine. And the products that we're going to try to get to through this loss of leaving group are a ketone and a chloride anion. Notice my carbon-chlorine bond has broken, and I originally had a carbon-oxygen single bond that is becoming a double bond. I'm going to have to account for all of these changes in my curved arrows. This particular example will have two curved arrows. I bring down a lone pair from oxygen to the middle of the carbon-oxygen bond, and my second curved arrow goes from the middle of the carbon-chlorine bond to chlorine. The first curved arrow is showing taking of a lone pair to make a pi bond, and that shows up in the products. And the second curved arrow breaks the carbon-chlorine bond and forms the chloride anion. Here as well, you want to carefully evaluate your starting material compared to products to figure out how many curved arrows you should have. The third type of curved arrow pattern is proton transfer, and we've seen this previously in Bronsted-Lowry acid-base reactions. As an example, let's consider having an alcohol starting material and NH2-. NH2- can serve as a base, and the products would be an alkoxide or oxygen anion, the conjugate base of an alcohol, and NH3. Notice that I'm breaking an oxygen-hydrogen bond and making a nitrogen-hydrogen bond in this reaction. I need to account for these two changes in my curved arrows. I take a nitrogen lone pair and form a new bond to the proton, break the OH bond, and move those electrons to oxygen. It's also possible for proton transfers to have more than two curved arrows, and I'm showing you a reaction where that will be the case below. I have a ketone starting material and NH2- again. Here I'm drawing my conjugate base, where I have a new carbon-carbon double bond, a carbon-oxygen single bond, and oxygen has a new lone pair and a negative charge. My conjugate acid is NH3. I would classify there being three main things that have happened here. A new NH bond has formed, a carbon-carbon pi bond has formed, and a new oxygen lone pair has been created. My curved arrow mechanism is going to have to account for all of these. Going from the starting materials to the products I showed you is actually going to take 3 curved arrows, all at the same time. I'll use a lone pair from my base to form a new bond to the proton. I'm going to take the electrons from the carbon-hydrogen bond and use them directly to form a carbon-carbon pi bond. Then I'm going to break the carbon-oxygen pi bond and bring those electrons up to oxygen. My first curved arrow starts at a lone pair and goes to an atom. My second curved arrow goes from the middle of a bond to the middle of another bond. And my third curved arrow goes from the middle of a pi bond up to oxygen. By drawing the curved arrows in this way for this proton transfer, I get directly to those products in the structures that they were drawn in. Our fourth and final curved arrow pattern is rearrangement, and we're going to focus on carbocation rearrangements. Before we get into those curved arrows, though, I want to tell you some things about carbocation stabilities. Recall that your carbocation is trigonal planar and sp2 hybridized, and it has an empty p orbital. As an example, let's consider what's known as the ethyl cation. Here I've drawn out the wedge and dash structure of the ethyl carbocation. The carbon with the positive charge has all of its bonds in a plane, and then the carbon with 4 bonds is tetrahedral. Perpendicular to the carbocation's plane of bonds is its empty p orbital. This has 2 lobes equal in size, but with opposite shadings. It turns out that having a CH3 group attached to the carbocation makes it more stable than if it just had hydrogens around it. The reason for this is that the neighboring CH bonds can donate some electron density. So here I've explicitly drawn out the sigma bonding orbital for the CH bond. I have an sp3 orbital from carbon overlapping with an s orbital from hydrogen. This sigma bonding orbital can share a little bit of its electron density with the carbocation by donating a little bit of electron density into the empty p orbital. We call this sharing of electrons hyperconjugation. The more alkyl groups with neighboring carbon-hydrogen bonds that you have around your carbocation, the more this type of hyperconjugation can occur. And hyperconjugation is a stabilizing effect. The concept of hyperconjugation explains the experimentally observed stabilities for carbocations, which differ based on how many R carbon groups are around them. The methyl carbocation, without any R groups around it, is the least stable carbocation. We'll call a carbocation with 1 carbon group and 2 hydrogens around it a primary carbocation. If you have 2 carbon groups attached to the carbocation, it will be called secondary. And if you have 3 carbon groups around it, it will be called tertiary. Going from no carbon groups to 1, to 2, to 3, your carbocation increases in stability the more of these carbon groups are around it. Carbocation rearrangements are going to occur in order to form a more stable carbocation. And there are two common types of carbocation rearrangements that we will see. The first of these is called a hydride shift, and it's going to involve a hydrogen moving with electrons from a CH bond to the neighboring carbocation. I would call this carbocation secondary because it has two carbon groups attached to it, and then there's also a hydrogen attached to it that's not drawn out. For the hydride shift I'm about to show, on a neighboring carbon from the carbocation, I've explicitly drawn out a CH bond. My curved arrow pattern for the hydride shift is going to involve a single curved arrow. I take the electrons from the CH bond and bring them to the carbocation. In the curved arrow language, this signifies that this CH bond broke, and the hydrogen as well as the electrons from the bond hopped over a position. So that red CH bond is now on the carbon that was formerly the carbocation, and then the carbon that lost its hydrogen now has a positive charge and is our new carbocation. Notice that this new carbocation is attached to three other carbons, so I could call it tertiary. My starting secondary carbocation is less stable than this new tertiary carbocation. This hydride shift would occur because it results in the formation of a more substituted and more stable carbocation, where substituted refers to carbon substituents instead of hydrogen ones. Another variant on a carbocation rearrangement is called an alkyl shift. This is where instead of a hydrogen moving, you have a carbon group moving with its electrons instead. Let's consider this closely related carbocation. The carbocation itself is secondary. Here, instead of having a CH bond at this position, I have a carbon methyl bond at that position. My alkyl shift will involve a single curved arrow. I take the electrons from the carbon-carbon bond and move them to the carbocation. This has the effect of breaking the original carbon-carbon bond and moving the CH3 group with the electrons to form a new carbon CH3 bond. The carbon that formerly had the methyl group attached to it lost a bond and became the new carbocation. I would classify this carbocation as tertiary because it has bonds to three carbons. This alkyl shift resulted in conversion of a less stable secondary carbocation into a more stable tertiary one, so I would predict that this carbocation rearrangement would occur. To end, I want to talk about reactions that involve more than one curved arrow pattern. If your reaction has multiple steps, you could have different combinations of curved arrow patterns possible within your mechanism. Let's consider the following reaction. What you want to do is, for each step of the reaction, you want to identify what's happening. I started out with an alcohol and HBr, and notice that in my first intermediate, I have a new oxygen-hydrogen bond and a bromide anion. In this particular case, I would have two curved arrows. I use the oxygen lone pair to form a new bond to the proton, break the HBr bond, and bring those electrons to bromine. This is an example of a proton transfer reaction. Now I have that conjugate acid of an alcohol as my intermediate, and going to the next intermediate, notice that I've broken my carbon-oxygen bond, I've formed a carbocation, and a water molecule. My curved arrow pattern needs to account for this carbon-oxygen bond breaking. I would draw this by taking the electrons from the carbon-oxygen bond and bringing them up to oxygen. This is an example of a loss of leaving group step. Now let's look at the final product. My water molecule has stayed the same, but my final product has a new carbon-bromine bond. To create this bond, I'm going to take electrons from bromine and use them to form a bond to the carbocation. This pattern is an example of a nucleophilic attack. All right, so to summarize, I introduced the ideas of nucleophiles and electrophiles as reagents that are going to tend to react together, with nucleophiles donating electron density to form new bonds to electrophiles. I talked about 4 curved arrow patterns, carbocation stability. That's it for this video. I will see you in class.